Hi, so in this video, we're going to look at expected values, but from the perspective of the binomial distribution. And we're really going to look at this through what's called an indicator function. And this is really going to help us kind of settle everything down and make things a little nicer and see where this our original expected value is kind of coming from. So if you think about this, when we're talking about the binomial distribution, right? It was kind of weird in that we weren't finding the expected value of one trial. We're finding an expected value of multiple trials, right? And so basically what we have is for the binomial distribution, what we did is we ran some trial n times, and each one of these times had a probability of success p, right? So this is kind of, I should do these in this note. We have n trials, and each has a success p. And so the question becomes, well, what happens if we just run one trial? Like, in essence, what happens with the Bernoulli distribution, right? So one trial is basically just the Bernoulli distribution. So here I'll add one trial is Bernoulli, right? And so we need to figure out what's a good way to represent this. And so if you think about it, our trial is either going to succeed or it's going to fail, right? It's either a yes or a no. That's it. There's no really other option. So what we can do is for this one trial, we can create some random variable. And we'll make the random variable be equal to x, right? So we make the random variable be x. And we say x is equal to 1 when we're successful, and it's 0 when it's not. So think of this as binary, right? 1 means we're good, we succeeded, we got this. 0 means we failed, like it did not work out. Okay, and this is actually called an indicator function because it indicates whether we succeeded or failed. Simple as that. It's telling us whether we got a good number or a bad number. Okay, so what's the expected value for this one trial? So what's the expected value for this indicator? So what do we have? We have expected value of x is the sum of all x, where probability of x is equal to x. So here we have two options, right? Either x is equal to 1 or x is equal to 0. So here we have 0 times the probability that x is equal to 0 plus 1 times the probability that x is equal to 1. Now, what did these two things mean, right? This meant event successful, which means the probability that this happens is p. This means event unsuccessful, right? Event unsuccessful. And that means we have probability 1 minus p, basically whatever's left over. So what do we have? We have 0 times 1 minus p plus 1 times p. Well, that just gives me p. So our expected value is p. Whatever p is, that's our expected value. Nice, like super nice and easy. So what happens if we run this n times, right? Let's go back to the binomial distribution. Let's see what happens if I take this distribution and then I do it n times. So every single time I do a trial, I'm basically doing one Bernoulli trial, right? So I can kind of represent each one with some indicator function. So we say xi is going to be the indicator function of the ith time I do this trial. So I do 1, 2, 3, 4, 5 trials. The fourth one is x4, for example. And each one is going to be successful, and if it's successful, we give it xi is equal to 1. If it's not successful, it's 0, etc. And here what we're going to want to do is we're going to want to use an expression, and here I'm not going to prove where this comes from. Don't worry about it. But we're going to use this summation, right? So this is really what we're trying to solve. We want to know how many of them succeed, right? If k of these are equal to 1, then we're looking at probability that x is equal to k. So this is kind of summing over all the different number k's that we can and what's the expected value, right? And so here what we have is this is actually equal to this. We can just sum all of the expected values with no problem. We just do the expected value of each one. This is called the linearity of expectation, The book kind of calls this the addition rule for expected value. I like the book naming for this better because it kind of sounds a little better. But in modern parlance, we call this linearity of expectations. So I'm going to use that from now on. And here, notice that this does not depend on whether the random values are independent or not. If they're independent, this works. If they're dependent, this works as well. There's no problem. So every time you see this, you can break this apart, and it's nice and easy. So then what do we have for binomial? So how about for binomial? What happens? For binomial, so I take my function, I take my expected value. I want to see what the expected value of all of these things are. Well, here I can just do expected value of each one, right? Since the trials are independent, we know each one has the same probability of p, and so we get p basically n times, right? So there's n of these. So this is just n times p. And this is basically where our expected value from before was coming from. It's basically this combination idea of summing over the expected value over all the probabilities, and then this linearity of expectation. And the cool thing about this, it gets even better, is that notice how here, like if they were independent, they each have the same p. But if they don't have the same p, this works just as well. Like if every single one of these were dependent, that like they all have different probabilities, we can have the same thing. So if I let xi have the probability of bi, so if I let e of xi be pi, so each one is kind of different, then I have this very similar thing, right? Xn, this is just the sum of x1 plus the expected value of x2 plus all the way up to xn. And so this is just p1 plus p2 plus all the way up to pn. So you can just sum over all the pi. So it's super nice and simple for that. Like it's gorgeous. Gorgeous. I don't know, I love it. I think it's cool as all hell. Okay, so we're gonna stop here before we do an example. In the next video, I'm gonna do an example or two, and hopefully that will help understand a little more where these things are coming from and how to kind of work with these. So I will see you in the next video. Bye.